Hi, this is John Whitaker for the Mathematical Analysis 2 class. And this, excuse me, this is video lecture number 21. And I want to start today by summing up a little bit about the series information that you've been given. And in particular, I wanted to say what kind of tests, series tests that we've had. Do they apply to complex or real sequences that we're adding up? And so the first thing we looked at was the Cauchy criterion series test, and that was for complex numbers. And of course, real numbers, that's for complex series. Of course, real numbers are also complex numbers. That's what that statement was about. We had the divergence test, and that's for complex series. We had something about the partial sums being bounded, and that's the only time that this series where a sub n was greater than or equal to 0 would be applied if only if the partial sums were bounded. That has to do with a series that has real terms being added. We had the comparison test, and had part A and B. And part A, the a sub n's that were involved, we had them inside absolute values, but that's really norm. And so the a sub n's involved in the first statement for the comparison test can be applied to complex numbers. And the c sub n is still part of the statement A for the comparison test. That has to be a real sequence. And in the second part for the comparison test about the divergence, that the sequences involved are sequences of real numbers. The geometric series test that we listed was for real numbers. Remember, x had to be between 0 and 1. There was that if and only if statement having to do with the series of a sub k's and comparing it to the series of 2 to the k, a subscript 2 to the k, and that had to do with real sequences involved in the series. The root test is for complex series, and the ratio test is for complex series. So that's what we had. I'd like to do some examples of where we can use these theorems. I'm just going to do them on series that have real numbers. So here's some collection of examples of series, and we're going to test whether they converge or diverge. So the first one I want to look at is the sum as n runs from 1 to infinity of 3 to the n plus 1 over 4 to the n plus 7. And the question is, does this converge or diverge? Okay, so here, I'm going to use the divergence test to show that this diverges. So if we take the limit as n goes to infinity of 3 to the n plus 1 over 4 to the n plus 7, look, this is a sequence that the bottom of the sequence, if you will, goes to infinity. So we can apply a L'Hopital rule if we think of these as functions. And that's the same thing as the limit as n goes to infinity of 3 over 4 is equal to 3 over 4. And so that is 0. It didn't converge to 0. The limit of the sequence didn't converge to 0. So that summation diverges by the divergence test. Now that's a type of problem that we would give to our Cal 2 students. So it's just a way that we're applying these tests. Okay, just a reminder. Second example, if we look at the sum as n runs from 1 to infinity of 1 over n to the 7th, that's a quick answer that that series converges by the p-series test. When I was talking about these tests, and I was talking about whether they apply to real series or complex series. I didn't mention the P series. The P series, of course, that's applying to a real, where we're summing up a sequence of real numbers. Okay, a third example. So we look at the sum as n runs from 1 to infinity of 1 over the square root of n. Then this is the same thing as the sum as n runs from 1 to infinity of 1 over n to the 1/2. And so this is a divergent P series. Okay. A fourth example is if we look at the sum as n runs from 1 to infinity of 1/4 raised to the n. This is a convergent geometric series. And that's by the geometric series test. And another example, I look at the sum as n runs from 1 to infinity of 3/2 raised to the n. This is a divergent geometric series. A sixth example, let's look at the sum as n runs from 1 to infinity of 1 over n squared plus 1. Okay, what I want to tell you is that the sequence that we're summing up looks a lot like 1 over n squared. And so that's what I'm going to compare it to. So I'm using the comparison test. And let's start off by, I'm going to say note that n squared plus 1 is going to be greater than n squared. And so that tells us that 1 over n squared plus 1 is going to be less than 1 over n squared. Now, look, you take the norm of this guy, it's just 1 over n squared plus 1. And so we apply the comparison test and say, since the sum is 1 over n squared, converges. And it converges because it's a P series. Then, the sum is n run from 1 to infinity of 1 over n squared plus 1 converges by the comparison test. It's that part A of the comparison test. And look, this statement right here is true for all n bigger than or equal to 1. So when we're wanting to know what that number was, the natural number is, which this statement holds true, it's from all of them, 1 and on. Okay. So another example I'd like to look at is if we look at the sum as n runs from 1 to infinity of 1 over n minus 1/2 times the square root of n. Okay, my claim is it's divergence. Okay, so here, the reason it's going to diverge, if we note that n minus 1 minus 1/2 times the square root of n, that's definitely less than n. Here, because we're taking away something positive from n, and so it got smaller. So n's bigger. Thus, it turns out for all natural numbers, n is going to be bigger than this number. So both of these quantities involved are positive. And so what we have is 1 over n is going to be less than 1 over n minus 1/2 and the square root of n. Okay, that's right. Okay, so since the series as n runs from 1 to infinity, 1 over n diverges, and that's by the p-series test, then this sum as n runs from 1 to infinity of 1 over n minus 1/2 times the square root of n, that will also diverge by the comparison test. Another example is if we consider the sum as n runs from 1 to infinity of 3 to the n over n factorial. A lot of times, series that involves n factorial, we're able to determine something about their convergence or divergence using the ratio test. That's what I'm going to look at here. I'm going to say, no, the lim sup as n goes to infinity of a sub n plus 1 over a sub n is really equal to the lim sup as n goes to infinity. So here, this will be 3 n plus 1 over n plus 1 factorial, all divided. So in this case, it is absolute value because these are real numbers. Here it's going to be 3 to the n over n factorial. That's equal to the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 factorial times the flip of this, it's n factorial over 3 to the n. And that's equal to, I should have written down lim sup here. That's the lim sup as n goes to infinity. Here, we'll cancel, and we're just left with 3 over, this will be just n plus 1. And that's equal to 3 times the lim sup as n goes to infinity of 1 over n. Now look, this sequence 1 over n goes to 0, so the lim sup goes to 0. So this is going to be equal to 3 times 0, which equals to 0. So that's our alpha, and our alpha is less than 1. So that says that this series, converges by the ratio test.
Okay.
The last example, if we will consider, so this is example 9, consider the sum as n runs from 1 to infinity of n over 2 n plus 3, all raised to n power. Okay. This is a problem that, because of this nth power being involved, that the root test will be advantageous that I use. So here I'll note that the lim sup, as n goes to infinity, of the nth root of the n over 2n plus 3 raised to the nth power will be equal to the lim sup as n goes to infinity. Here, the nth root and the nth power will cancel with each other, and we just have n. This should have been in absolute values here, but because everything's positive, we just get n over 2n plus 3. Now, look, the lim sup of this is really the same thing as the limit of this. And this is going to be equal to 1/2. You can use L'Hopital's rule to get that. And so what we have is that this series converges by the root test. Okay. So those are some examples of series that they converge on. Okay, next thing I want to do is write the definition. Next, what this is given a sequence C sub n of complex numbers the series is n runs from 0 to infinity of C sub n, so I guess here I'll start from 0. C sub n, Z to n is called a power series. So Z is just some complex number, okay? And you fix complex number. Okay, the numbers C sub n are called the coefficients of the series. And Z, as I said, is a complex number. What we're interested in is we want to know for which complex numbers Z will the power series C sub n times Z raised n converge and really diverge. So that's what we're interested in. Here's a theorem. It says, given the power series sum as the sum of C sub n to Z sub n, we put infinity of the nth root of the norm of c sub n's, and we define r to be equal to 1 over alpha, and here we might have some questions about certain situations. And so what we say is if alpha was equal to 0, then r is going to be equal to plus infinity. Okay? That's that situation. And if alpha is equal to infinity, then we're going to say r is equal to 0 in that case. All right, so here's the conclusions of the theorem. It says then this power series of c sub n times c to the n converges if the norm of z is less than this number r, or this quantity r, and diverges if the norm of z is bigger than r. Okay, so we're ready to do the proof. And kind of for shorthand notation, what we'll do is we'll let a sub n be equal to c sub n times z of n. So that short notation say then we are concerned with the convergence or divergence of the sum of the a sub n's, and that's what we're interested in. Now, the statement that we wrote looks a lot like the root test, and that's what we're going to be applying. So we will apply the root test. To this sum. Okay. So what we look at is we know the lim sup as n goes to infinity of the nth root of the norm of a sub n. Okay. Well, I guess reverting back to the notation of what a sub n represents, we have the nth root of the norm of c sub n z raised to the n. This is equal to the lim sup as n goes to infinity. Here, this will be the nth root. We break this into the norm of c sub n times the norm of z raised to the n, and that's the lim sup as n goes to infinity. Here, this will be the nth root of the norm of c sub n times the norm of c raised to the n. And that's equal to the lim sup. Okay, the nth root of c sub n is the nth root of the norm of c sub n, so I can't simplify that. But the nth root of the norm of z is just the norm of z. So I'll put that out front. That's equal to the lim sup as n goes to infinity. Well, I can pull out the z because of the norm of z because it doesn't fit on n of the nth root of c sub n. Okay. Now that's the guy we called alpha in our theorem. Okay. 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 So here this is then going to be equal to norm of z. Okay. And then this is the the alpha, and so R is equal to 1 over alpha, so this is really equal to norm of Z over R. And then by the root test, so by the root test, okay, if the norm of Z over R is less than 1, that means that the norm of Z is going to be less than R. Then that means that the sum of the C sub n, Z raised to the n, converges. If this norm of Z over R is greater than 1, then this sum of the C sub n, Z sub n diverges. And that, of course, is by the root test. That's what the theorem said. Okay, great. So this previous theorem is what we just did, implies that for every power series, there exists, let's call the power series the sum of the C sub n z's to the n. There exists an R, it's an extended real number possibly, such that this power series converges if the norm of Z is less than R, and diverges if the norm of Z is bigger than R. We can say something about what if R is infinity. Here we mean, in that case, that this norm is infinite. Okay. Then, okay, great. Okay. And this is true, well, we wouldn't understand, because the limb soup, as n goes to infinity, of this nth root of the norm of C sub n, Z sub n, that always exists. I'd be infinity, but that always exists, okay? It's a number, it's infinity. Okay? So if we can make a definition, what we'll say is, given a series of power series, that's the C sub n, Z raised to the n. Here we're adding n right from 0 to infinity. What we're thinking of is 0 to the 0 is going to be 1, is what we're looking at. Okay. The extended real number R such that, what about R? This series converges if the norm of Z is less than R, and diverges if the norm of Z is bigger than R, is called the radius of convergence for this power series. So kind of thinking in the complex plane, essentially what we're doing is we're drawing a circle centered at the origin whose radius is R, and everything within that circle, every complex number within that circle, that power series will converge, and everything outside that circle, the power series will diverge. And we're not saying what happens on the border of the circle. Okay? It might converge, it might diverge.
Okay.
Let's look at some examples, and these are straight out of the text. So the text lists 5. I'm going to do 4 of them that they list. Here, as examples, let's look at the series as n runs from 0, the power series n runs from 0 to infinity of n raised to the n, z to the n. Again, 0 to 0 we're going to define to be 1 in this case. So I want us to note the lim sup as n goes to infinity of the nth root of the n raised to the n z to the n. This is equal to the lim sup as n goes to infinity. Okay, this will be the nth root of n to the n z's norm raised to the n. It's equal to the lim sup of n times the norm of z. The norm of z can be pulled out. Okay, and that's equal to infinity. So that's our alpha. And so r was 1 over alpha. So in this case, we have that r is 0. Okay. That is, this power series converges only when z is equal to 0. Okay? That's the only time that the, well, this guy is less than 0, if you will, or less than or equal to 0. So here, this power series converges. Equal to 0. Okay, it says less than, but here with this special case of r being equal to 0, we have less than or equal to 0. The power series will always converge at 0. You have the 0 raised to powers. And most of those are going to be 0 except when the power is 0. Okay, our second example is that the sum as n runs from 0 to infinity of z sub n over n factorial. That's our second example. And here, essentially we want to know for what z values is this going to converge. And we will use the ratio test, using the ratio test. To find z's such that this series converges. We examine the limb suit as n goes to infinity. Here it's z to the n plus 1 over n plus 1 factorial, the norm of that, over z to the n over n factorial. And that's equal to the limb suit as n goes to infinity of z to the n plus 1 over n plus 1 factorial times the flip of the bottom, which is n factorial over z to the n. And then that says we have the limb suit as n goes to infinity. Here, this is the same thing as the norm of z all over, it would be n plus 1, which is the norm of z times the limb suit of 1 over n plus 1. And look, this limb suit is going to be 0, and so this just gets 0 times the norm of z, which is 0. And so here's what we're saying. This series, so r is equal to plus infinity. Okay? And what that says is then this power series converges for all z, for all complex numbers. As a third example, we're going to look at the series of just z to the n. This is n runs from 0 to infinity. And here we note that the limit as n goes to infinity, the limit suit, so I'm using the root test here, of the nth root, or the previous theorem, of here it would be 1, okay? So that's the c sub n's here. That's the c sub n's. That's going to be equal to the limb suit as n goes to infinity of just 1 equal to 1. Okay. And so the radius of convergence is equal to 1. Now, that tells us, thus, if the norm of z is less than 1, then if the norm of z is less than 1, then this series, power series, converges. And if the norm of z is bigger than 1, the series diverges. That's by the previous statement. And if the norm of z equals to 1, then the series, this particular series, sum as n runs from 0 to infinity of z to n, is going to diverge as the limit as n goes to infinity of z to the n can't be equal to 0. So it's divergent by the divergence test. And I'd like to say a little bit more about that. Okay. And so, I'm going to say more about it.
Well, we'll do a proof by contradiction
Here, if we suppose okay. So what I'll say is because if the limit as n went to infinity of z sub n equal to 0, then there would exist remember, we're in this case where we're assuming the norm of z is equal to 1. There exists a natural number n, call it big N, such that for all n bigger than or equal to big N, the norm of z to the n minus 0 will be less than any positive number. Let's pick 1/2. That's our epsilon. So that says for all n bigger than or equal to this big N, we'd have, well, z sub n minus 0 is just z sub n. The norm of z sub n is the norm of z raised to the n. That would be less than 1/2. But the norm of z in this case is 1. So we'd have 1 raised to the n, which is 1, is less than 1/2. And that's a contradiction. So that says that the z sub n can't go to 0. Okay, so the fourth example I'd like to look at is we'll consider the sum of z sub n over n squared. And then, in particular, note, we'll consider the lim sup as n goes to infinity of the nth root of 1 over n squared. So that's what we're going to look at. But the way I'm going to look at it is examining the limit as n goes to infinity of the nth root of 1 over n squared, which is the same thing as the limit as n goes to infinity of n raised to the minus 2 over n. Okay. And actually, I'm not going to look at this particular limit. I'm going to look at the limit of Ln. Now, that's Ln. And that's going to be equal to, by rules of logarithm, that's the limit as n goes to infinity of minus 2 over n times Ln of n. And that's going to be equal to the limit as n goes to infinity of minus 2 times Ln of n over n. Now, this bottom is going towards infinity, so we can apply L'Hopital rule. So that's equal to the limit as n goes to infinity of minus 2 times 1 over n times 1, and that goes to 0. Okay, so the limit as n goes to infinity of just, we did ln of this nth root. So just the nth root of 1 over n squared, that's going to be equal to e to the 0, which equals to 1. Okay? Now, since this limit is equal to 1, that means every subsequence of it will also converge to 1. So that says the lim sup as n goes to infinity of the nth root of 1 over n squared, that's going to be equal to 1. Okay? So it means r is equal to 1 by that previous theorem. And so this series of z, so the series was z to the n over n squared converges if the norm of z is less than 1 and diverges if the norm of z is bigger than 1. And so now we're going to address the question, what happens if the norm of z is equal to 1? So if the norm of z equals to 1, okay, then when we look at z raised to n over n squared, that's going to be equal to, well, the norm of z raised to n over n squared, which equals to 1 over n squared. Okay? That's what this guy is. So we have that the norm of zn over n squared is less than or equal to 1 over n squared. And the sum of 1 over n squared here, let's say is n runs from 1 to 50, this guy converges. So what can you tell me about what can we tell about the sum of the z sub n over n squared when n is equal to 1? This guy's got to converge, okay, by the comparison test. So that's what we have. Okay, I've got one more theorem to write up, and we'll use this in the future. But here's what it says. It says, given two sequences, okay, a sub n runs from 0 to infinity, and b sub n runs from 0 to infinity. Okay, we put a sub n, big A sub n, is like the partial sums. It's the sum as k runs from 0 to n of a sub k, so the partial sums of the a, the little a's, and we put a sub minus 1, we're going to define it to be 0. Then, if we have 0 is less than or equal to p is less than or equal to q, we have, and I need a little bit more room to write the conclusion. Here it is. We have, okay, so here's the conclusion. The sum as n runs from p to q of a sub n times b to n, this is going to be equal to the sum as n runs from P to Q minus 1 of this big A sub n, B sub n minus B sub n plus 1, and outside the sum is plus A sub Q B sub Q minus A sub P minus 1 B sub P. Okay, so let's look at the proof. We're going to let A sub n be equal to the partial sums of the little a's. And that's what we're going to have if n is greater than or equal to 0. And we're going to put A subscript minus 1 equal to 0. Okay. Here's something to notice, and that, if you have this index r, and it's bigger than 1, then if you want to say A sub little r, the rth term in that sequence, little a's, well, that's really equal to the sum as k runs from 0 to r of A sub k minus the sum as k runs from 0 to r, r minus 1, I should say, of A sub k's. Okay? And that's equal to A sub n, or I should say A sub r, minus A sub r minus 1, big A's. And if r equals to 0, then we have A sub 0 is equal to the sum as k runs from 0 to 0 of A sub k minus 0, and then that's equal to A sub 0, okay, minus A sub minus 1, okay, because A sub minus 1 is defined to be 0. And that's really giving us A sub r, because r is 0 in this case, minus A sub r minus 1. So in all cases, for when r is greater than or equal to 0, we have that A sub r is equal to big A sub r minus big A sub r minus 1. That's what the notation indicates.
Okay.
All right. Thus, what we're looking to show in this formula, the summation is n runs from P to Q of the A sub n times B sub n. That's going to be equal to the sum is n runs from P to Q. This will be A sub n minus A sub n minus 1, what we just did with the big A's, and then time B sub n. And then that's going to be equal to the sum as n runs from P to Q of A sub n B times B sub n minus the sum as n runs from P to Q of A sub n minus 1 B sub n. Okay, now what I'm going to do for this second sum is kind of make a change of variables. So this guy I'm going to leave alone. And here I'm going to let, so I'm going to write this, I'm going to let j equal to n minus 1. And so this is minus, and we have this sum, just rewriting it with this index. It's j runs from, well, j is 1 less than what n would. So it would be from p minus 1 up to q minus 1. So 1 less than n. Okay. And then here, wherever I see n minus 1, I can put a j. So it's a sub j. And here, n is the same thing as j plus 1. We just solve for n right there. That's what we get. Then we might as well switch back to the notation of index of n again. So this is a sub n times b sub n minus. And so here, let's just let n be equal to j. And here we have the sum. N is equal to j in what I'm thinking. We have the sum as n runs from p minus 1 to q minus 1. This will be a sub n, b sub n plus 1. That's what we have. Now, this is the last line. And this is equal to, okay, here, when you look at these two sums, they match very well, except this guy starts at one lower, okay? And this guy finishes with one more. So a lot of the terms that we're adding up are the same, okay? And so here, this will be the sum as n runs from p up to q minus 1, okay? So for those guys, they're exactly the same. And then I have a sub n, b sub n, minus a sub n, b sub n minus 1. So I'll just pull out an a sub n, and I'll have b sub n minus b sub n plus 1. That's what I should have said. And then what we're missing is we're missing the first term when n is equal to p here. And so that's a sub p minus 1. And then when n is equal to p, this will be p. Okay? And then that's this term. That should be a minus, okay? And we're also missing this term when n is equal to k. So that's plus a, not k, q. A sub q, b sub q. And that's exactly what we wanted to show. So that's the proof. And we'll use that in some later results. That's enough for this lecture. Thank you very much.